All right, welcome to a pretty difficult physics problem, but over and over in this problem, although things look scary, we're going to be going back to basics just over and over and over. First, let's just read the problem. A 2-kilogram block and an 8-kilogram block are both attached to an ideal spring for which the spring stiffness constant is 200 newtons per meter, and both are initially at rest on horizontal frictionless surface. That's going to be important, as shown in the diagram above. In an initial experiment, a 100-gram ball of clay, that's right here, is thrown at the 2-kilogram block. The clay is moving horizontally with speed v, unknown as of now, when it hits and sticks to the block. That will be important as well. The 8-kilogram block is held still by a removable stop. Removable is going to become important in the later stages of this problem. As a result, the spring compresses a maximum distance of 0.4 meters. Calculate the energy stored in the spring at maximum compression. There are two equations that you need to know when it comes to springs. Spring equations are these. First of all, there's what's called Hooke's law, but if you don't know what that's called, that's fine. That's F equals negative kx, where this right here is the force that the spring exerts to try to get back to its normal shape. And this right here multiplies the spring constant by the degree to which the spring is either compressed or extended. The reason for the minus sign is that the spring will try to deform in the opposite direction from how it's been deformed initially. So say that you compress the spring. Well, the spring will not try to exert a force that compresses it more. It'll exert a force that tries to extend or restore its original shape. So this is sometimes called the restorative force, and it needs to be in the opposite direction for the deformation. Okay, but this equation is not the one that we actually need. That was just a review of spring equations. This is the one that we're really going to be using, that the energy stored in a spring, which is always a form of potential energy, because it's energy that can be turned into motion. If the spring is let loose, then it turns into kinetic energy. Energy that can be turned into kinetic energy is the definition of potential energy. Put that into your brain. So you can say US, meaning potential energy stored in the spring. You can also say like UEL or PE. EL, there's a bunch of ways to write it. Don't let anybody tell you you're wrong because you write things a certain way. That's just a way of writing it. But US equals 1/2 kx squared. This equation right here is going to be the one that we use because we are told the spring constant, and we're also told the amount to which the spring is deformed. So we're going to be using this equation, and US is going to be 1/2 times the spring constant of 200 newtons per meter times 0.4 meters squared. Half of 200 is 100. 0.4 squared is 0.16 because 4 times 4 is 16. Give it 2 decimal places. So this is 100 times 0.16, which is 16. It's a unit of energy, so it's joules. Okay, let's go to part B on the next page. Now, calculate the speed of the clay ball and 2-kilogram block immediately after the clay sticks to the block, but before the spring compresses significantly. Before the spring compresses significantly means when all energy is still kinetic. If all the energy is still kinetic, that means that we have not started to store energy in the spring yet. So this is, remember, if you're studying physics and calculus at the same time, which you may be, this is an instantaneous reality that at this point, all of the energy that used to be stored in the ball is now stored either in the block or has been dissipated elsewhere. And now we're looking just at the amount of energy that's in the block plus clay ball system. Okay, so that's the significance of that. the speed of the clay ball and 2 kilogram block immediately after the clay sticks. Well, okay, this means that the potential energy of the spring, when it's maximized, has to be equal to the kinetic energy of the, I'll call this B1, meaning the ball and block put together. So KE of B1. We already know this. This is 16 joules. And that's going to be equal to 1/2 times the M, the mass of B1, times its velocity squared. Now, just to be clear, I'm contrasting the potential energy that gets stored in the spring here with the kinetic energy of the block when it begins to compress the spring. So these are at different points in time, but because of conservation of energy, you should know that the amount of energy that the spring has eventually stored in it needs to be equal to the amount of energy that the block plus ball system had when it began to compress the spring. So these are different points in time. This is when the block first begins to move, combined with the ball. And then this is the potential energy. This is the time when the spring is fully compressed. The reason these two are equal is not because of some fancy equation where they're always equal. It's just conservation of energy. So on the left side here, there is no more kinetic energy because all of it's been converted to potential. On the right side, there's no potential because at this point, no energy has started to be stored in the spring yet. Sound good? Okay, let's keep going. We know this. The mass of B1 is 2.1 kilograms, not 2, because the clay ball has stuck to the thing. So this will be 16 equals half of 2.1 times V squared. Isolating V, we get V equals 16 times 2 is 32. And then divide that by 2.1, take a square root of that, and yep, this right here be a calculator problem. So square root of 3.2 or 32 over 2.1, and this will be 3.9 meters per second. Okay, so this is pretty easy so far. Let's go on to part C. Calculate the initial speed V of the clay. Now, when I first looked at this problem, I was like, oh, another conservation of energy step. No big deal. But actually, it's not. It's not. This is trickier because in C, we are dealing with an inelastic collision. An inelastic collision is when objects stick together. In fact, it gets an even more specific name. It is a totally inelastic collision. This is a collision where the two things don't hit each other and bounce off and go their separate ways, or they hit and one stops and falls dead and transfers all its momentum to the other. This is one where the two things hit each other, and then instead of going their separate ways, they actually stick together and begin to move together. Well, this specifically means that kinetic energy is not conserved. So the kinetic energy that's present in the ball does not completely transfer to the block. But although that means we cannot use conservation of energy, we can always use conservation of momentum. So momentum is always conserved regardless of whether the collision is elastic or not. Now, I want to say something here. Conservation of energy is a valid principle. It's just that sometimes the energy transfer is a more complicated thing than just simple interactions between two things. So the clay ball splats against this block, and its kinetic energy does go into the block, but it also goes elsewhere. It deforms the clay ball, most notably. So it used to be that the clay ball is this big round thing, but then it splats onto the block, and now it's like, a big pancake on the block. So that actually takes energy. In order to turn this into this, you need to exert a certain amount of energy. The difference between the kinetic energy that the ball possessed when it was flying toward the block and the kinetic energy that gets effectively transferred to the block does weird, strange things like deform the ball into a pancake shape. Or maybe it creates a small amount of heat as it dissipates in doing that. So we're not going to be able to use conservation of energy, but we can use conservation of momentum. So let's say this collision right here between these two, we're going to look at as a momentum style collision, not a conservation of energy style collision. And momentum, which I've never understood why it was shown with the letter P, but it just is. So P of the ball, and this is before the collision, must be equal to P of what we've been calling B1, where B1 is the two of them put together. And this is after the collision. Now, everybody and his brother knows that momentum is Martha's Vineyard, right? MV, mass times velocity. So let's put those in here. The momentum of the ball is going to be the mass of the ball times the velocity of the ball. And oh, look, it's the thing we're looking for. And this is going to be equal to the mass of B1 times the velocity of B1. Keep in mind that this is before the collision and this is after. So I'll just note that specifically. This is before and this is after. Now let's put in what we know so that we can solve for what we don't. The mass of the ball is a known quantity. It's 0.1 kilograms. The velocity of the ball is the thing we want to solve for. So we don't know it yet, but we will soon. The mass of B1 is 2.1 kilograms. And the velocity of B1, well, we don't know that, do we? Except we just solved for it. It's right up here. It's the 3.9. Okay, so this is 3.9. Because there's only one thing that we don't know, we can isolate it, and then we're all set. 2.1 times 3.9 divided by 0.1, which is to say times 10. And so we've got 2.1 times 3.9 divided by 0.1 is a shockingly high 81.9 meters per second. This is much, much faster than what you would get if you analyze the same problem using simple conservation of energy. Again, I made the mistake of doing that when I first looked at this, but then I found that it was suspiciously low. And I was like, that can't really be right. Yeah, it needs conservation of momentum. Now, why the heck is the ball going so fast? It's going so fast because in order to get the entire system moving, keep in mind that all of the momentum is initially concentrated in this super tiny thing. And tiny means the amount of mass. 0.1 kilograms is a small, small amount of mass. But in order for it to start moving stuff, it needs to be going wicked fast. So the 0.1 kilograms doesn't have a lot of what you would call momentum density, which is what mass is. But it does, in order to get the system moving, need a lot of momentum, what you could call volume, which is velocity. So 81.9 meters per second, very fast, but it is the only thing that works for this. Let's move on to part D. State whether the maximum compression of the spring will be greater than, equal to, or less than 0.4 meters under these conditions. So in a second experiment, an identical ball of clay is thrown at another identical 2-kilogram block, but this time the stop, this thing right here, is removed so that the 8-kilogram block is free to move. Well, think about this. In the initial circumstance, this block compresses the spring, okay? And that energy has nowhere to go. It just gets trapped in the spring, and then it'll eventually launch outward and it will, start this thing bouncing back and forth. But now we've changed the situation. As this spring compresses, it will exert a restorative force in both directions. So as the spring compresses, it will exert a force this way and a force this way. We've already taken into account the fact that the block is going to be able to overcome this restorative force. So it's going to squinch down the spring like, by some amount. But now this restorative force exerted in this direction is going to be capable of moving this 8-kilogram block. So think about it. Spring still gets squinched the same amount from this direction, but now it's able to relieve some of that pressure by pushing the 8-kilogram block out of the way. This means that it will not compress as much. So it will not compress as much because it's able to dissipate some of the energy into the 8-kilogram block. And this is done by moving it as it compresses. Now, this is not to say that the spring does not compress at all. That's different. What this does say is that as the spring compresses, it'll compress on what in this picture is the left-hand side, but it will also be able to extend on the right-hand side. Because the 8-kilogram block is going to move a little bit more sluggishly, there will be an initial compression, but eventually the spring will be able to restore its prior shape. And that is the topic of part E. Now, in part E, when I first looked at this problem, I was like, I don't know what the hell's going on here. But if you get back to basics, then actually you can solve this pretty easily. So this says, state the principle or principles that can be used to calculate the velocity of the 8-kilogram block at the instant that the spring regains its original length. This regains its original length thing is going to be important. We're going to come back to that. Write the appropriate equation or equations and show the numerical substitutions, but do not solve for the velocity. Typically, when the test problem says do not solve for the velocity, it's because it would be too damn difficult to do so. So you should just keep in mind, like maybe there's going to be some horrible system of equations, something along those lines. So principle or principles, we are going to do not just one, but two principles. Because let's say that I initially, try to use conservation of energy. So conservation of energy. Well, this would tell me that at all times, total mechanical energy is 16 joules, because we know that that much is what was available at the beginning. That's the initial speed of the 2-kilogram block after the ball of clay has hit it. So B1 has that many joules of energy. Okay, so at all times, the total mechanical energy is 16 joules. If the spring has no deformation, then the potential energy currently stored in the spring is 0. Think about it for a second. Although the spring may be moving, it doesn't currently store any energy if it's at its original non-deformed length. Yes? Of course, yes. So that means that the kinetic energy stored in the B1 plus the kinetic energy stored in the B2 has to be the total available mechanical energy of 16 joules. Well, now it's just a matter of turning these into like MVs. So I'm going to have 1/2 MB1 times VB1 squared plus 1/2 MB2 times VB2 squared, and that will be equal to 16. Now it's a matter of checking and seeing what I know and what I don't. I know M1 or MB1. I know the mass of B2 as well. And now I run into a problem because I do not know the other two quantities. This and this are both unknown. Now, this would be a very sad ending to the story, except we have something to save us. And this is also, this is another principle. So first of all, we used conservation of energy. We found that it would be insufficient to solve for the unknown quantity. However, watch this, we can also use conservation of momentum. Now, to be clear, we're not talking about any collisions here, right? But think about the fact that the momentum of B1, where this is right after the ball collides, has to be equal to the momentum present in the system at all subsequent times. And in particular, we're going to look at the time when the spring is no longer deformed. So now we'll be looking at MB1 VB1 plus MB2 VB2. And because we're looking at the same instant in time, that means that VB1 and VB2 mean the same thing both times, or mean the same thing in both equations. So now think back to, just basic algebra. However many unknowns you have to solve for, you need that number of equations in order to solve for them. So before, we saw that we had two unknowns. There was VB1 and VB2. Well, that was bad news because we had two unknowns, but just one equation. This is a very typical physics setup. If it seems like you don't have enough information, sometimes it means that you're not applying enough principles. So this applies conservation of energy, and it's two variables. And it's like, oh, that tastes too hard. I need another equation. Well, the other equation you get by applying another principle. The question does say plug in the numbers, even though you don't have to actually solve for it all the way. So let's get energy. First of all, 1/2, 1/2. Well, I was going to say 1/2, that would cancel, but actually we'll just keep the 1/2s. So energy can be 1/2 times 2.1 times VB1 squared plus 1/2 times 8. Oh, like mass of B2, right? Times VB2 squared. And then momentum would be MB1 times VB1. Those are known quantities. This is 2.1 times 3.9. Remember that from way back? Yeah. And that's going to be equal to MB1, which is 2.1 times VB1. And then that'll be plus MB2, or 8, times VB2. At this point, we have sufficient information to solve for VB2, which is what we were really after the whole time. Notice how we didn't solve for it, but the system is present with two variables, exactly what we need in order to solve for the two variables. Easy peasy.